Hey, what's up, guys? Yeah, so today I want to prove another interesting probability inequality called Pinsker's inequality. Okay, and if you want to see more inequality, that you can check out my maybe useful for your research or whatever. You can check out my list below. Hope you guys subscribe to my channel. Okay, so this Pinsker's inequality is a hard proof that I checked. I found it, then I found the proof online is none of them are trivial. Okay. Okay, so I want to give the maybe I think it's still not trivial but interesting proof. So it's not the best proof, but I think it's very interesting. So my starting point is that I define PQ are some probability distribution, and for the easiness, I define it just to be finite. But you can change into continuous version. You can define a so-called KOL divergence, which is P over Q, defined to be a summation of QI log of PI log of QI. Okay, let's say sum over I, where I is a omega. Okay, and you can define a BPQ. This is called the total. This is the variable distance for a non-total version. Basically, just sum over I, PI, QI. Okay, so Pinsker's inequality tell you that your KL divergence is greater or equal to half of BPQ squared. So this is the version. Okay, so you can view these inequalities purely algebra. Right? Somebody tell you that the PI sum from I from maybe 1 to D, whatever is probably the vector sum from 1, QI from 1 to D is probably the vector, and all these zero probably results, and you want to plug this DKL and the VPQ and ask, oh, whether this is true or not. So you can make it just purely algebra. Oh, but we need this one. And yeah, so the proof is non-trivial, so we need to go through the proof. Okay, so proof. Now I need to use like two facts that none of them are trivial. Okay, but let's maybe tell you the lemma 1, lemma 2. Okay, so lemma 2 is very simple. Lemma 2 is another theorem called T2's lemma. So if you haven't seen my other videos, that I recommend to see this T2's lemma proof. Basically, it's very simple. Start from some AI, BI, I from 1 maybe n. Although BI should be non-zero, and then you take BI. Yeah, BI should be positive. Right, from 1 n, this guy will greater equal to summation AI squared, summation BI. Okay, so this is called T2's lemma. Okay, so proof is very simple. Proof just Cauchy-Schwarz. So you just start from AI square root of BI. And then let's say you square. And I from 1 to maybe n. And you take the square root of BI squared. I from 1 to n. So greater equal to summation of AI squared. Okay, so Cauchy-Schwarz. And so this guy will be summation of BI from 1 to n. So just throw away. Throw to the right hand side, then you get a result. Okay, so remember it's T2's lemma is what we want. Okay, and there's a lemma 1 that I think is very trivial. Is that the following function? The following function is greater or equal to 0. Okay, so what function is that 1 plus r log 1 plus r minus r minus r squared divided by 2, 1 plus r divided by 3. Let's call this f of r. So my claim is that f of r is greater or equal to 0 when r greater than minus 1. Okay, then you can check that when r equals minus 1, that this guy will be 0 times infinity, then you can play around with L'Hopital 0. And then so r equals minus 1 will be positive. Okay, but this is our lemma. So you can play around with calculus if you try to prove it. Okay, but yeah, but I will not. Then let me just describe the proof. Okay, so you can just do some computer series. You can just play around with this, plot this 1 plus r log 1 plus r minus r minus half of r squared 1 plus r divided by 3 and plot it, right? You can see it's positive. Or you can just so this is some figure that make you believe what I'm saying is true. But we need these two derivatives. So let me just using these two derivatives. Okay. So the only thing, let me just copy the derivative. Yeah, I already copied. So let me just yeah, let me just put a derivative here. Over so where's the derivative? Oh, not good. Let me just do some derivative. I guess maybe here. Yeah, I mean, yeah, okay. So this is the derivative f prime and the f of double prime. Okay. So our goal is to show that the f of r is greater than 0, right? So let's consider r is greater than 0 and then consider f of r is 0. Then by the mean value theorem, we know there's r1 with r, right? And the f of 0 that you can plot. Let's consider. So let's compute f of 0. That 1 times log 1 minus 0 minus 0, so that's 0. Okay, so this guy is 0. Okay, now we calculate, but not obvious to see that f of prime is greater or equal to 0 or not. Okay, so now let's consider f prime r 1 minus f of 0, f prime of 0 that equal to f double prime of r2 r1. Okay, and then okay, so f prime of 0 and f prime of 0 where 0 plus 0 is 0. Okay, so this guy is 0. Okay, so combine these two, we get f of r equals to f of double prime r2 r1 and r. Okay, so now consider r greater than 0, which means that r1 is greater than 0, which means that we only need to prove that the double prime of r2 is less than 0, greater than 0. So this is the second derivative. If you expand it, you will see that the mysterious thing happened. This is r cubed plus 9r squared plus 27r plus 27 minus 27 minus 27r divided by this. Okay, so very easy to see this. Okay, so your numerator is r squared plus 9r squared. So obviously that when r greater than 0, then this guy will greater than 0. Okay, so we proved that the second derivative is greater than 0, which proves that f of r is greater than 0. Okay, then now you can consider r is equal to 0. So when r equals 0, then you get f of 0, 0. We know this. Now let's consider r greater than minus 1. And you can do this when r less than minus 0, and then you use these two lines that which r1 is negative, right? R is negative, so both are negative, and you're asking the same thing where the second derivative is greater than or equal to 0. And obviously then r cubed plus 9r squared is greater than 0. Right? You can check r cubed plus 9r squared is greater than equal to 0 when r is less than greater or equal to minus 1. Okay. Very easy to prove. Okay. So now we have proposed these two powerful lemma, and now we can prove this Pinsker's inequality trivially. Okay. So now remember these two lemma, and we are going to dive into the proof. Okay, so let's go to proof. Okay, so write down our KL. Okay, so remember it's pi log pi qi. Okay, actually one can write this as expectation value of q of this 1 plus r log 1 plus r minus 1r, where r is p divided by q, where p divided by q. Sometimes I use capital Q, sometimes I use lowercase q, but it's the same. Okay, so why this is true? Let me just tell you. So why this is true, and then you just do the expansion. So let's do this. So the summation of q, right? So I qi. So 1 plus r is just pi divided by qi. 1 plus r, right? So you get pi qi log pi qi minus pi qi plus 1. So that I pi log pi minus qi minus summation of I pi summation of I. These are two probability vectors. They are both 1. Okay, so this guy is exactly tail divergence. Okay, so using lemma 1, this expectation value 1 plus r log 1 plus r minus r is greater or equal to, as we just proved, right? It's greater or equal to this. Okay, so it's greater or equal to expectation value EQ r squared divided by 1 plus r divided by 3. Okay. Now one can use. Okay, so now one can use T2's lemma. Okay, so one can use T2's lemma. Okay, so this guy will be greater or equal to the expectation value EQ. So remember that the T2's lemma looks like this. Okay, so when you do the expectation value of r squared divided by the numerator, then this will be take the absolute value on the numerator divided by denominator. So this guy will be EQ the absolute value of r. Okay, and take the square and divided by expectation value of EQ plus 1 divided by 1 plus r divided by 3. Okay. Okay. So now let me just write down the right hand side. Okay, so right hand side is greater or equal to half of EQ r squared. EQ is EQ r squared and the EQ 1 plus r divided by 3. Okay. So very simple check is that EQ 1 plus r divided by 3 is actually 1. But the reason is very simple, because EQ of 1 plus just 1 plus 1/3 pi q p divided by q minus 1, right? So it's 1/3 p divided by q, the EQ plus 2 divided by 3, and this guy is just 1 divided by 3. Okay, so it's 1. Okay, so it's half of EQ r squared, which is what? Half of summation I qi. These are just pi minus qi minus 1 and the square. Half of summation I pi minus qi square. Half, this is just divided VPQ divided by 2. Okay, so VPQ divided by 2 is less or equal to, is the VQ divided by 2 square is less or equal to square, right? So square is less or equal to the tail divergence. Okay, so this is a Pinsker's inequality that using the two following to some simple square. So these two T2's lemma and these strange functions proof. I mean, there's other proof that you can use that Bernoulli. You can first consider Bernoulli variable and do something weird thing. Yeah, hopefully you can still get proof. But this proof, I think this Pinsker's lemma is Pinsker's inequality is very non-trivial. That how can we come up with this kind of proof? I mean, it's very difficult that you write down this algebraically, very hard. Okay, hopefully this helps you guys.